Hello students, welcome to this module on which is part 3 in our series on Rayleigh-Plateau or the capillary instability. What we are going to do in this module is to discuss the stability analysis of a very viscous liquid, cylindrical liquid jet. Okay, and in the previous module, what we did was to analyze the case of an inviscid jet, and here we are going to take the opposite limit of what is commonly called the creeping flow limit. Here we are going to ignore inertial effects in the fluid. Okay, and so in that limit, when there is no inertia, the governing equations are called the Stokes equations, which are the Navier-Stokes equations without the inertial terms. All the terms multiplying the density of the fluid are set to 0, and it's incompressible. And the base state is that of a stationary fluid. As I told you, even if the jet is moving with a constant plug-like velocity, we can assume that the velocity is 0 by going in a frame of reference that is with the same velocity as the jet velocity. So we can, without loss of generality, consider a stationary fluid. Okay. Now, and the pressure inside the stationary jet, of course, is given by the outside pressure plus gamma by A. This is as before. This is the Young-Laplace equation for a cylinder, for an infinite cylinder. Now, the linearized equations well, there is no need for linearizing because the Stokes equations are by nature linear, because all the nonlinearities are in the inertial terms, which we are ignoring. So the linearized equations, the continuity equation. So I'm going to use the shorthand notation, and I'm going to use normal mode. So any velocity is denoted as e to the st, e to the ikx. Now, for the sake of simplicity, I'm going to assume only axisymmetric disturbances. I'm going to consider n equal to 0. So I'm going to restrict myself to axisymmetric disturbances, because as we saw in the previous module, non-axisymmetric disturbances are stable. Surface tension is stabilizing for non-axisymmetric disturbances, so we'll restrict ourselves to axisymmetric disturbances. So the continuity equation in cylindrical coordinates, okay, plus ikvz plus I and R inverse V theta is 0. Then the R momentum equation plus the viscosity mu times dr squared plus R inverse dr minus R to the minus 2 minus k squared. The Z momentum equation these are all straightforward application of the normal mode expansion to the operators in the cylindrical coordinate system of the Stokes equations. Okay, so the theta momentum equation okay. So we're going to consider only axisymmetric disturbances, as I just mentioned, right? And so we don't have to worry about the theta component at all, So because we are considering axisymmetric, we need not consider the theta momentum equation at all. So we can just consider these two equations, and we're going to set n equal to 0. Okay, and when we do this, you get a slightly simpler set of differential equations, and we can eliminate pressure by multiplying this equation by ik, and by taking the derivative of this equation, and by subtracting you can eliminate pressure. And when you do that, you will get dr operating on dr squared plus r inverse dr minus k squared. So what we are doing is we are differentiating the z momentum equation with respect to r, and we are multiplying the r momentum equation with respect to minus ik, so that this will become minus ik drp, this will become plus ik drp, it will cancel, right? We are eliminating pressure, so eliminating pressure, k squared Vz minus ik dr squared plus r inverse dr minus r to the minus 2 minus k squared operating on Vr is 0, right? Now what we can do is we can differentiate this whole expression using this dr. So I'll write dr squared, but I'm going to eventually write everything in terms of dr Vz plus r inverse dr minus r to the minus 2 minus k squared dr Vz, right? And let me operating on dr Vz. If you look at the second term, this everything is the same, so I can take this entire operator common. I can write it as minus ik Vr is 0. Now if I use the continuity equation, Vz is I by k dr plus r inverse Vr. This is the continuity equation. So dr Vz is I by k okay. So we'll substitute this back out here, so we'll get dr squared. I'm writing this equation, dr squared plus r inverse dr operating on, now there is an I by k. I'm going to pull out I by k, so we'll get dr squared plus r inverse dr minus r to the minus 2. Now because I'm pulling out I over k, I'll get minus k squared operating on Vr is 0, or you can simply write this as dr squared plus r inverse dr whole squared operating on Vr is 0. This is the final governing equation to be solved in the limit of 0 inertia. Okay. Now the solutions are Vr of r is nothing but C1 r. These are again, I'm sorry about this. Okay, sorry about the glitch. Okay, the solution of this equation can be written in terms of Bessel functions. So we'll have Vr of r is nothing but C1r k naught of kr plus C2r I naught of kr plus C3 k1 of kr plus C4 I1 of kr, and these are, because it's a fourth order differential equation, there are 4 linearly independent solutions. This is a fourth order ordinary differential equation. There are 4 linearly independent solutions. Okay. Now these two solutions diverge as r goes to 0, so we can set the constants to 0, and therefore Vr of r has only 2 constants. plus C4 I1 of KR. From this we can calculate Vz of R from the continuity equation. This is the continuity equation for axisymmetric case. Okay, and from there you can relate, because we know VR from here, we know VR, we can find Vz. The pressure is obtained from the X or Z momentum equation, and out from there you can find that the pressure is mu by Ik dr squared plus R inverse dr minus k squared operating on Vz. So first you find VR in terms of these two constants, then Vz in terms of the same two constants by differentiating VR, and pressure further by differentiating Vz. Okay, so the boundary conditions at R is equal to A plus zeta as before. Okay, are now, previously we had just the pressure at A, plus now the viscous stresses, the normal viscous stresses also become important, is gamma by A squared times 1 minus A squared K squared operating on zeta. Now zeta times S is equal to VR at A. Okay, that is from the kinematic condition. So this is the first boundary condition, the normal stress condition. The shear stress vanishes at the liquid gas interface. So this is again at R equal to A. So you have two constants. You have actually three constants, C1, C2 and zeta, but then zeta can be written in terms of VR using the kinematic condition. So you essentially have all represented in terms of two constants. You have two boundary conditions, so here instead of zeta I can put VR by S. Okay, now everything can be found in terms of the two constants and Bessel functions. So if you substitute this in these two boundary conditions at the interface, you will get everything in terms of, you can write it in terms of a matrix in terms of C2 and C4, where the first row is the normal stress balance, that is equation 1 here, and the second row is the tangential stress balance, that is equation 2 here. Okay, this is the normal stress balance. Okay, and everything is in terms of C2 and C4, so this has to be equal to 0. Now this is a homogeneous system of equation, and in order for this to have non-trivial solutions, remember that we need non-trivial solutions. Therefore we have to set, let's call the determinant of, let's call this matrix as M, then we'll have to set determinant of M equal to 0. Now because this conditions will have S, these coefficients will have S in them, so this will give rise to an equation, a polynomial for S. In this particular case it should be a linear equation, okay, in terms of where S is written in terms of K, A, and then mu and so on. Okay, mu, gamma and so on. Okay, and so you can plot this using a software like MATLAB once you get the expression. So mu A by gamma times S, which is a function of K, this is basically making it non-dimensional, times Ka will give you something like this. This is 1. So here as K goes to 0 or Ka goes to 0, the growth rate saturates, unlike the previous case, the inviscid case, where if you remember the growth rate started off with 0 and then went in like this, right, again went to 0. Now here it's not like that, and that's because of the fact that you have ignored inertia. Okay, even putting a very small inertia will change this behavior as k goes to 0. Okay, now this is how one calculates for a viscous jet, right? Now if you ask the question, if we are doing finite, you need not have an infinite jet all the time. Here we are assuming, so far we have assumed everything to be infinite. You could have a finite jet, that is, you could have two rigid surfaces and you could have a so-called capillary bridge, okay, of length L and radius R0. This is called a capillary bridge. Okay, a liquid bridge or a capillary bridge. Again, you can perturb R0 plus epsilon cos kz. Now the key thing is 0 less than z less than L. Z is not infinite, unlike in the previous case, because we considered so far infinite jets. So this means that if I consider the perturbations along the z direction, this is z is equal to 0, z is equal to L, you can only have waves that satisfy, see, the liquid makes a particular angle which is called the contact angle with the rigid surface, and in this particular case let's say that the contact angle is pi by 2, it's 90 degrees. Okay, now that means that it should always be 90 degrees. Okay, so you should have waves like this or like this or like this. So you can only fit an integral number of half wavelengths within this particular domain z is equal to 0 to L. So that means that n by 2 half lambda, this is how the wavelength takes discrete values, where n goes from 1, 2, 3, 4. Sorry, this is n times half lambda should be L0. Okay, or if I say n times lambda by 2 pi is L0 by pi, this can be thought of as the wave number, which is related to the wave number. K is 2 pi by lambda. Okay, so Kn, okay, is, so we can think of Kn, okay, if you think of this as Kn, okay, then Kn, from the Kn times n times Kn is L0 by pi, or Kn is L0 by n pi, n is 1, 2, 3 and so on. So it is discretized because you cannot fit arbitrarily, because of the boundary conditions at z is equal to 0 and L, you can only have a finite number of waves that can be fit in. Okay, this is a typical consequence of not having infinite boundaries. Okay, now this means that you can carry out the area and volume due to these deformations. So the area of the deformed sphere is 2 pi r L0 plus 1 by 2, like what we did, pi r epsilon squared k squared L0. L0 is the length of the cylinder. Okay, and the volume is pi r squared L0 plus half pi epsilon squared L0, but this is also the same as pi r0 squared L0. This is the conservation of volume. This gives us an expression between relation between r and r0. Okay, now the change in area is nothing but a minus 2 pi r0 L0 is nothing but half pi L0 by r0 epsilon squared n squared pi squared r0 squared minus 1. And you can see that the area the change in area is it can be positive or negative depending on the competition between these terms. But in any case, if you want it to be negative, this term has to be beaten by -1. So n is 1 is the least stable. Okay. Now if you put n is equal to 1, then delta A is negative if pi squared r naught squared by L naught squared is less than 1. Okay. Right? Or, so this is the unstable case, pi r naught is less than L naught. Okay. Now if the other way around, if L naught, this is unstable, if L naught is less than pi r naught, then this is a stable, because the area, this other way around, the area is going to increase due to these deformations, and such configurations are energetically not favorable. Okay, so this is a rough qualitative explanation of how one carries out the stability of a finite bridge. The key aspect being that you cannot fit in arbitrary wave numbers. You have to fit in the largest wavelength, or is determined by the size of the domain in the z direction, and that will set the type of waves that can be fit into this domain. Okay, so this is how one does viscous capillary jets, as well as for jets with finite domains, okay, finite lengths. I'll stop here and I'll continue in the next module. Thank you.